Hello everybody, we're back. We're going to be talking about chapter 3, first couple of sections. And we're going to focus on the idea of the random variable. All right, and let's define a random variable. It is a variable whose values are determined by chance. Are determined by chance. All right, there are two types of random variables. There's the discrete random variable, and the discrete random variable is countable. Right? We talked about discrete already. All right, so give some examples. Right? The rolling of a die, tossing of a coin are all discrete because you got to go from 1 to 2 to 3. You can't have half a toss of a coin. Number of joggers in a park. Can't have half a jogger. That would be quite messy. The other type of random variable is a continuous random variable. And the continuous random variable, remember, takes all the values. So for example, temperature. All right, because you can go from 60 to 60.1, 0.2, 0.3, and all the values in between. Weight is also another one. And height are all examples of a continuous random variable. All right, so we talked about that already. So let's give an example of, let's say, tossing a coin 3 times. And if we toss a coin 3 times, and let's say we want to count the number of heads, we can quantify that in a couple of different ways. So for example, I can do it by sample space, which we already talked about. I can say 0 heads is going to be tail, tail, tail. I could say 1 head is going to be tail, tail, head, tail, head, tail, and head, tail, tail. So there are 3 options there. Or I could say 2 heads would be head, head, tail, head, tail, head, and tail, head, head. So again, 3 options. Then I could say I could have 3 heads. There's only 1 option, head, head, head. Now, as far as sample space goes, it is a good way to do it. However, if you're let's say it's tossing a coin 5 times or 10 times or 12 times, sample space becomes quite large. So we've developed something called a probability distribution. And in a probability distribution, we have x, which is the number of heads, and the probability of x. So if I say x is the number of heads, I can have 0 heads. In our, just like our last example, I could have 0 heads. I could have 1 head. I could have 2, or I could have 3. Now let's take a look at the sample space. I have 0. So how many total do I have in my sample space? I have 1, 2, 3, 4, 5, 6, 7, 8. So the probability of getting 0 heads would be 1 out of 8. Probability of 1 head would be 1, 2, 3. So 3 out of, excuse me for a second, I can't write the 8. Let's try that again. 3 out of 8. For 2 heads, again, would be 3 out of 8. And for 3 heads would be 1 out of, 1 second, 1 out of, can't write the 8, hang on. There we go, 1 out of 8. All right, now, there are some requirements for a probability distribution. All right, the first requirement is that P of x is a number between 0 and 1. Second requirement is area always adds up to 1. So let's take a look at our probability distribution here. I've got 1/8 plus 3/8 plus 3/8 plus 1/8. Do a quick addition. That adds you up to 1. Now there are a variety of different types of probability distributions. The first type is called a discrete uniform distribution. And I'll give an example of rolling a die. All right. If we were to put this in a probability distribution, my x values are going to be 1, 2, 3, 4, 5, and 6. And why don't you pause the video now to write down your probabilities of getting each number. All right, hopefully you got 1/6 for 1, 1/6 for 2, 1/6 for all of them. And the reason it's called a uniform distribution is if you were to graph this, you're going to make a better graph than me. Right? All of the little things would be at the same height of 1/6. That's why it is called uniform. Another word for this particular type of probability distribution is called a probability mass function. Or it's called, for short, probability mass function. All right. again, most people use probability distribution, but on the off chance that they say make a probability mass function, you should know what they mean. Now, there is another type of probability distribution called a cumulative distribution function. And we're going to use the same example we used before of tossing a coin. Now, I'm just going to create the graph first this time. Actually, you know what? Let's make my graph a little bit longer. There we go. So this is 1/6. 1/3, 1/2. So that's 1/6, 2/6, 3/6, 4/6, 5/6, and 6/6 is 1. So the probability of rolling a 1 is 1/6. Now, with a cumulative distribution function, all right, we talk about not just the probability of rolling a 2, but rolling a 2 or less. So the probability of rolling a 2 or less is 2/6. Probability of rolling a 3 or less is 3/6. Basically, you take that probability and add it to the prior probabilities. So we have a 4, 4/6, 5 would be 5/6. And again, it's not just probability of rolling a 6, it's probability of rolling a 6 or less. And that would again be the guaranteed event or 1. So that is basically what we do, is we accumulate our probability. So the actual, that's the graph, the actual cumulative distribution function for rolling a die would look something like this. So probability of x being less than or equal to 1. Probability of x less than or equal to 2. Probability of x less than or equal to 3. So it takes into account all the prior probabilities. Less than or equal to 4. So again, this would be 1/6, 2/6, which would be 1/3. 3/6, which would be 1/2, because I'm taking the 1/6, right? Because if I'm saying probability of x, right, of rolling less than or equal to 3, I can roll a 3, I could roll a 2, I could roll a 1. So there's 3 potential numbers I could roll out of a possible 6 numbers. Probability of x less than or equal to 6. So for 4/6, 5/6, and 6/6. All right. So the cumulative distribution function, as I've stated, takes into account not just the probability of 3, but everything prior to 3 as well. All right. So if I were to ask you, here's an example. What is the probability of rolling of 5 or higher. All right, so if I say 5 or higher, I could say 1 minus the probability of x being less than or equal to 4. That would give me 5 or higher. And I can look on my cumulative distribution function and say, what's the probability of less than or equal to 4? That's 2/3. So I could say 1 minus 2/3, which equals 1/3. So depending on your situation, you could use your cumulative distribution function to your advantage. All right. So here I have a choice. Which of the following are probability distribution functions? Following, are so A would be f of x equals 0.25, x equals 9, 10, 11, 12. B would be f of x equals 3 minus x over 2. X would equal 1, 2, 3, and 4. C would be x squared plus x plus 1 over 25. X equals 0, 1, 2, 3. All right, so why don't you pause the video? Why don't you take a look at these three and pick which one is a probability distribution. All right, so hopefully you paused the video and we can take a look. Now, in order to be a probability distribution, all right, let's take a look at all three of them. So let's look at A. So I have x and p of x. So x is 9, 10, 11, 12. And p of x is 0.25, 0.25, 0.25, 0.25. Now remember, there were two requirements for a probability distribution. The first is that all the probabilities are positive, and in this case, that is true. The second is all the probabilities add up to 1. All right, those are the two requirements for a probability distribution function. And in this case, A fulfills both requirements, so yes, it is a probability distribution function. All right, let's go to B. Let's take a look at B. So B, right, if I have my x, p of x, so my x would be 1, 2, 3, and 4. And my p of x was the function 3 minus x over 2. So I'm going to take each x and I'm going to run it through my function. Why don't you pause the video? Do that now. All right, so hopefully you calculated. So this would be 1.0. This would be 0.5. This would be 0. And this would be negative 0.5. Now, this would add up to 1 for sure. However, my probability right here is negative, and that just can't happen. So I would say no for choice B. All right, for choice C, all right, let's give it a little space for choice C. That would be P of x equals x squared plus x plus 1 over 25 for x equaling 0, 1, 2, and 3. All right, so I'm going to make my probability function. So I got 0, 1, 2, and 3. And I'm going to take each one of those numbers, plug them in. So why don't you pause the video now, take each one of these numbers, plug them into your function, and get me a probability. All right, so hopefully you plugged them in. And for 0, I got 1 over 25. For 1, I got 3 over 25. For 2, I got 7 over 25. And for 3, I got 13 over 25. Now, here's the good part. None of them are negative this time. However, if you add up all the probabilities, they only add up to 24 out of 25. So being that the sum does not add up to 1, we cannot call this a probability distribution. So that would be a no. All right. So let's do an example real quick about using a probability distribution. The number of ships to arrive at a harbor on any given day is a random variable represented by x. The probability mass function is I got 10, 11, 12, 13, 14. All right. And I got 0.4, 0.2, 0.2, 0.1, 0.1. All right. So we want to A, find the probability exactly 14 ships arrive. Find the probability that exactly 14 ships arrive. So what I want to know is, what is the probability that x equals 14? And if I look on my chart, x equals 14 at 0.1. Not 0, 1, 1. All right. B, at least 12 ships. Arrive. All right. Now again, the setup is probably the hardest part of this, because if I say at least 12 ships, I want to know the probability that x is going to be greater than or equal to 12. I want 12 to be the lowest number of ships, but there could be 13 or 14 ships. And in that case, I have to add up the probability of 12 plus the probability of 13 plus the probability of 14, which would be 0.4. All right, and lastly, I got to move it up. I want to know the probability that at most 11 ships arrive. And if it's at most 11 ships arrive, I want to know the probability that x is going to be less than or equal to 11, right? If at most 11 ships arrive, 11 is the biggest number we can have. All right, so probability of 11 is 0.2, probability of 10, 0.4. So this probability would be 0.6. All right, so you can really just read the graph at times and do your job. All right, so let's do another example. You ask 1,000 people to pick a number. Between 1 and 10. Got to tell you what the numbers are between. Assuming picks are random. How many people pick 9? All right, well, if I'm saying x and p of x, right, and x are the numbers I could pick, which would be 1, 2, 3, 4, 5, 6, 7, 9, and 10. Why don't you pause the video and put in the probabilities of each number? All right, so hopefully you said for any one person picking these numbers, if they were truly random, your probability would be 1/10 because there's 10 numbers and they're picking one. All right, however, we have 1,000 people. So we have 1,000 people picking numbers. So if I have 1,000 people picking numbers, I'm going to multiply that times my probability of picking a 9. And how many people do I expect should be picking a 9? 100 people. Should pick a 9. Always got to put in some sort of a sentence. All right? So my second question would be, let's extend this example. What percentage of people do you expect to pick a number less than or equal to 6? So that would be the probability that x is less than or equal to 6, right? And that would be 1/10, 1/10, 1/10, 1/10, 1/10, 1, 2, 3, 4, 5, 1/10. So that would be 0.6. So what percentage of students would it be? It would be 60% of people. Right? And whatever sentence that you would create. All right, we have two more ideas to go through. The first is expected value. All right, expected value is another way to say the mean. All right, so we could say the mean equals the expected value, and the formula for that is x times p of x. So the sigma is always sum of. So let's talk about the lottery. All right. So a lottery works by picking six numbers from 1 to 49. It costs $1 to play, but you could win $2 million. All right, so the question is, what is my expected value from playing the lottery? Well, if I just play once, right, I could either lose $1 by losing the lottery, or I could win $2 million. All right, so the question is, now I need to know my probability of winning the lottery or not winning the lottery. Why don't you pause the video, think about it, and we'll work on it in just a second. Okay, so if I need to know, in order to get the probability, I need to know how I could pick 6 numbers out of 49. All right, and I'm using a combination because this lottery, it doesn't care about the order. And in general, lotteries don't care about the order. They just want you to get the 6 numbers in some sort of order. So why don't you pause the video and do 49 combination 6, and I'll see you on the back end. All right, I did 49C6, and I got 13,983,816. So the probability of winning the lottery is 1 over 13,983,816. Or if I wanted to change that to a decimal, I could say 7.2 times 10 to the negative 8th, which is a very, very small percentage of winning. All right. And I could do 1 minus that for my percentage of losing, which would be 0.99991, 2, 3, 4, 5, 6, 7 nines. All right. So now if I wanted to know my expected value, right? My expected value would be the probability of winning times my 2 million bucks, my prize money, plus the probability of losing times the price to lose, which would be I'd lose $1. So why don't you pause the video, work this out, and I'll see you on the back end with the answer. All right, so I worked it out to be negative 0.86. So over the long haul, you would expect to lose 86 cents if you were to play just once. Now, let's say you want to play once a week. You say, hey man, you got to be in it to win it. So I'm going to play once a week for the next 10 years. All right. Basically, what you do is you take how many weeks are there in 10 years. If there's 52 weeks in a year, it's 520 weeks in 10 years. But I'm going to multiply that times negative 0.86. And I got it to be negative $447.20. So if you were to play $1 a week for 520 weeks, out of pocket you would be spending $520, but you would expect to lose $447.20, which means at certain times you're going to win some money. And basically what people just say, hey, got to be in it to win it. I won money. I'm going to play more. What you don't realize is that every time you shell out money, right? So you, over the long haul, will expect to lose over $400. All right. So the last thing we need to talk about is variance. So variance for a probability distribution. All right, so variance again is sigma squared equals the sum of x squared times p of x minus mu Standard deviation would be the square root of your variance. All right, so let's do just one last example. All right, so my probability distribution for tossing a die, right, rolling a dice. I have x, p of x, remember I told you any die is always going to be standard. All right. So if I wanted to find my standard deviation or my variance, let's just go with variance because standard deviation is just the square root of that. It's going to be the sum of x squared times p of x. So that's 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6 plus 4 squared times 1/6 plus 5 squared times 1/6 plus 6 squared times 1/6 minus my mu, and I'm going to give you mu. Mu was 3.5. All right, I got to revise something real quick. Should be mu squared. So down here should be 3.5 squared. So why don't you guys take a few minutes to work that out on your calculator. I'll give you the answer on the back end. Pause the video. All right, hopefully you paused the video. Now the key here is all this stuff has to go into the calculator, and if you put in your parentheses wrong or you mistype something, all right, you could get a number. It could just be a wrong one. The number should be 2.9 for the variance. And if you took the square root for your standard deviation, it should be about 1.7. So that's our discussion for sections 1 through 3. All right, so at this point, you're gonna stop the video, and I will see you in class. Thanks, guys.